Welcome to Team 3's High-Speed Radar-Launched UAS project presentation. We will be discussing the analysis and findings made during this project and will give suggestions to our best design outcomes. The project goal is to design a turbine engine and a radar bracket system that will be integrated onto the Rebel Hot RC Sport Jet. This will enable the aircraft to take off from a launch rail and climb to Mach 0.25 at initial cruise. The aircraft will have a combat radius of 5 nautical miles and will operate at 10,000 feet for the majority of the flight. A big emphasis on the mission profile is to produce a maximized loiter time. The mission analysis was developed within MathCAD and is based upon the equations provided. A list of the weights of the aircraft is shown. The takeoff weight is found by adding fuel weight, aircraft empty weight, and the weight of the radar bracket. Then all other legs are found based on the Brugger range equation. Finally, the free body diagram demonstrates the analysis used to find takeoff calculations for the kinematic portion of the mission analysis.
This graph displays the drag polar and TSFC trends based on velocity for the Rebel Hot RC aircraft. In our mission analysis, we determined the minimum aerodynamic drag point to occur around 200 feet per second. Coincidentally, this is close to the mission requirement of 269 feet per second at an altitude of 10,000 feet for the initial high-speed cruise mission leg. A future recommendation for missions involving this aircraft would be to fly at this minimum drag point. In order to determine the equation relating the aerodynamic drag to velocity, a number of tools were used, including XFoil, MathCAD, and the benchmarking of aerodynamic characteristics of other aircraft.
After several iterations of engines, the final engine was chosen from the carpet plot shown in the top left corner. The black dot represents the rubber engine that was chosen in size for the mission. It had a PIC of 2.5 with an operating turbine temperature of 1650 degrees Rankine and a max of 1950 degrees Rankine. The engine was designed to be less than or equivalent to modern small turbojets on the market. With lower levels of technology to match current engines, the performance will suffer, having larger TSFCs and less available specific thrust. But the design can be completed on time, be affordable, and be maintained or replaced with ease. The performance of the engine was less than desirable, as shown in the Mach sweeps on the left, with thrust versus Mach on the top and TSFC versus Mach on the bottom, along with the throttle hooks on the right displaying the relationship between TSFC and thrust at 5, 10, 15, and 20,000 feet altitude at differing Mach numbers. With this engine being small and inefficient, the optimum throttle position is 100% throughout the mission. But since little thrust is needed for the majority of the legs, 100% throttle only affects the durability of the engine, not the mission.
Upon completion of the HSIS portion of the engine performance analysis, the additive drag was calculated using the equation shown. Then the actual installation losses were found using these additive drag values. These installation losses, along with the actual thrust-specific fuel consumptions, were then plugged back into the mission analysis. In this way, we are accounting for the actual losses rather than those previously assumed in the RFP.
Next up is a rocket design. We ended up going with a 3 grain per motor design with a rocket diameter of 50.8 millimeters, or about 2 inches. These criteria were needed to achieve an impulse of 555.7 newton seconds per rocket. This will allow us to maintain our flight path angle of 10 degrees and will allow us to have a launch angle of 19 degrees. These rockets will have a burnout time of 2.16 seconds with a velocity of about 280 miles per hour.
Issues faced in airframe integration are the design of a mounting bracket for the rocket, a retention pin to hold the aircraft into place until the rocket reaches the required thrust, preventing the aircraft from hitting the launch rail, a way for the bracket to detach from the aircraft, and a recovery system for the rocket and bracket after it detaches. For the bracket, our final design weight was 0.8 pounds, with a spring pull connection to mount the bracket to the aircraft that will release during flight. To allow for a reloadable rocket motor, a screw-off nozzle has been implemented into the bracket. The launch rails were spaced out and support poles were crafted for the rails to prevent snags and collisions during launch. A retention pin made of ABS plastic with a diameter of 0.1 inches was designed to shear at the required takeoff velocity. Finally, after the bracket detaches, a parachute will be deployed from a custom 3D printed nose system that will allow for easy recovery and reuse of the bracket.
For bracket analysis, the rockets are angled at 19 degrees so the thrust vector adds through the CG of the aircraft. The 2 rockets designed give an average thrust of 116 pounds and are attached to the carbon fiber bracket. For strength, plate stringers are attached internally to the spar to assist in load distribution and structural stability of the aircraft, which assisted in the design of the inboard fuselage and wing structure. The inboard connection of the fuselage to the wings, as pictured here, will be made of carbon fiber for weight and strength capabilities. The 3 connection points from the spars are shown as well and are perpendicular to the fuselage. These tensions will be able to withstand the maximum applied loads due to lift and stress forces throughout the fuselage.
The spars and ribs are made of carbon fiber, while the skin is made of fiberglass. There were a few integration issues. The landing gear prevented a constant 3-spar design throughout the wing. To account for this, a channel for the landing gear was created, while open shear caused by the aileron made the structure unsafe. A trailing edge spar was introduced to close the gap. The design process consisted of a few steps, all of which used a worst-case load scenario of 5.75. With all of that in mind, the first step was to choose a spar design, then do analysis on the spar design as well as figure out placement, then do analysis on the wing boxes. All additions to the structure accounted for 36% of the weight, spars, 9% of the weight, ribs, while the rest of the weight was in the skin and miscellaneous structures. All stress analysis was done at the midspan of the wing. In doing so, the largest forces were accounted for. This gave a margin of safety of 2,500% caused by the low stress on the material and gave maximum shear flow and bending of our spars.